Hello, good afternoon. I am Mathias Fink, professor at École Physique Chimie in Paris, and I will speak of wave control for wireless communication. Let us go on my screen and let us begin here. Okay, I will discuss both of time reversal processing and reconfigurable intelligent surface are different approach that can play a role for 6G in the future. As you know, when you send a microwave in a city, you have really a complex media. It is not free space where wave propagate as easily. It is a medium where you have a lot of reverberation, scattering, because there are many obstacles. And in fact, inside a room or in a city, the wave field has a random nature. It is the sum of many scattered waves. And this has some behavior that is not so easy to see. For example, if we are not working with microwave light in optics, if you send a beam of light in a glass of milk, which is full of small scatterers, you know that on the screen behind the glass of milk, you will have many bright spots and dark spots. This is called the speckled pattern. And usually when you see this kind of pattern, because you have sent one frequency in the medium, you know that you can define what is called the coherence length, the distance between two bright spots. And you know also that you can define a coherence frequency. It means that if you change the frequency of the light you send in the milk for another color, the pattern will change completely. And these two concepts are important to understand how a wave propagated in a complex medium. Now, you have also this in a room. If you are, for example, in a kind of cavity, it can be a leaky cavity like an office. If you look at one frequency, what is the signal you observe if one antenna is emitting only one frequency, you have bright spot and black spot. It's a speckled pattern. And if you are at a good position, you are at the nodes of the field and you are happy, you can receive a message. But if you are at a bad position, the signal is small. And you can also define what is called a coherence length and also a coherence frequency that tell you that if you change the frequency of your emitter from a small amount, that is to say the coherence frequency, you will observe in the room a completely new pattern. This is quite important to know this because when you are doing communication, if you send from an antenna a signal, which is modulated by some information, you have to know if the bandwidth that you have remain in the coherence frequency of your room or not. Once you say this, what is important to know is that to solve this problem of communication in a complex medium, you can use the MIMO concept, multiple inputs, that is to say multiple antenna and multiple output, multiple antenna and receive. And you can ask, what is the efficiency of my communication in a city, for example? And you can use many antenna where each antenna has its own controller, own electronic circuits, and you can play with this and you can measure between each emitting antenna and each receiving antenna what we call the transmission matrix that give you the amplitude and phase that you receive on each antenna coming from each input antenna and taking into account all multiple reverberation in your medium. This matrix is a set of complex number. Each of them has an amplitude and a phase. Now, if you imagine that you work only at one frequency, a very narrow band signal, you are in the case of what we call monochromatic signal. And if you imagine that you want to improve communication between a set of antenna located at R1, R2, R3, and you want to send a message at point R. You know that if antenna R1 emits alone a signal, it will be an omnidirectional antenna. And here you have a random medium. Here, what you will receive on this plane is a random pattern. The amplitude of a field will be random with bright spot and black spot, as I explained before. Now, if you use the second antenna that emits at the same frequency of signal, if you look the pattern you will have behind the medium, it is also a random field, but which is uncorrelated with this one if the two antennas are at a distance bigger than the coherence length of the scattered field. Now, the same if you have antenna R3 emitting the signal alone, you will also observe on this plane a random pattern. Now, what we are interested is what happens if the three antennas emit together in phase. If you just make the summation of all the signal coming from these three antennas, it will be also a random pattern, and you will be not happy. At this point, nothing happened because you have just add all this pattern without matching the phase. Each of the signal arrive at point R with a given phase. Here I present a Fresnel vector with a given phase coming from R1, from R2, it's another phase. And if you make the summation, it's not very efficient. You send more energy, but the signal is not really better. And in fact, what is interesting is to ask, what is the best configuration for these three antennas to optimize the signal you receive at R? The best thing is to decide that you play on this spatial diversity where you have three antennas at three different spatial positions. But now, instead of sending the same sinusoidal signal on each antenna, you send the phase conjugated of R1 and R, but the phase conjugated of R2 and R, the phase conjugated of R3 and R, and in this case, because you have spatial reciprocity, you have the same path between R1 and R and R and R1. If you are doing this, you see that suddenly there is an accumulation of signal at point R because you have in fact put all the phase aligned at point R. And depending on the number of points you have, the number of antenna, if you just phase conjugated all the elementary impulse response, you will have a very strong signal and you can have a very good signal to noise for this point. This is called phase conjugation, and this used spatial diversity, that is to say many antenna. Now, you can also say, I have only one antenna, but now I use to make communication broadband signal. It is not what we are doing in 5G, but it is interesting to see. If you are really broadband signal, that is to say, if you send from one antenna many different frequencies, and if these frequencies are larger than the frequency coherence of your medium, you can do the following. If you have only one antenna at point R2, if you just emit one color, one frequency omega-1, you have a pattern here which is blue with speckled spot everywhere. And all these patterns oscillate at frequency omega-1. Now, imagine that you send another frequency, omega-2. It is another time frequency, and you will obtain for this color, which is different, another pattern that oscillates at frequency omega-2. If you send also a third color, green, with different frequency omega-3, you will observe a speckled pattern, green, which oscillates at frequency omega-3. And if you send all these signals together, it means that you send a short pulse whose Fourier decomposition is a set of different frequencies. And if you look now what you have at one point here, when you send a short pulse, which is the summation of all this, you will observe the summation of each speckled color, each oscillating at a different frequency, omega I. And what you observe at one time is a field. And if you observe now in the time domain, you see that you observe a long coda. You have sent a short pulse, but because of this medium, now the short pulse become very long because you have multipath in this medium. And you receive here a signal which is spread in time. And this signal is not really focused. It's a kind of noisy in space and noisy in time. Now, can you send something better from this point? Instead of sending a short pulse, now you can send another signal. If you take this signal that you receive here, if you time reverse this signal, and if you send it from this point, now you send exactly this in reverse. Now something magical occurs. You sending this, it is like you phase conjugated each signal at each frequency. And now, instead of receiving all these sinusoidal waves that arrive with random phase, if you send them exactly in the reverse order, when you look what you receive here, there is a magic time for which you receive suddenly a big peak. And we call this time focusing. It's happened only at one time. And the size is the size of a speckled grain. And you have made double focusing, spatial temporal focusing. And when you send this signal, here you receive a short peak, which is very well focused in space and time. Now, can we use this concept to make communication? In fact, when you have many antennas, you have spatial diversity, but if also you have many frequencies at your disposal, because you work with very broadband signal, how many spatial frequency degree of freedom I have? If I have 5 antennas, I have 5 spatial positions where I send spatial uncorrelated signal. If I have many frequencies which are uncorrelated, I have many frequencies. And I have a number of spatial frequency degree of freedom that can be big. Even if the number of antennas is small, if I have many frequencies, I have many degree of freedoms, and I can play with this. And in the past, in our lab, we play with this to make telecommunication, but with ultrasound through very complex medium. The medium we have was a forest of wires where when you send waves, it is completely randomly spread in the medium because of multiple reverberation. And for example, if you have a point source that sends a wave, short pulse, through this random medium, if here you have a set of antennas, like in a MIMO configuration, you have many antennas, each receive a long coda because of the reverberation in this medium. Now, if later you take all this signal and you time reverse all this signal and you send back by each antenna that become now a transmitter, now you will have a time reversal signal that will refocus back in space and time. And when you send all this complex signal at this location, which is the original point, everything recompressed in time. And if you look the size of a focal spot, the size becomes very thin. You have a focal spot here that you obtain when you have these 5 antennas, which is here 35 times thinner than what will happen if you have a medium without scatterers. And you find a very interesting property of time reversal or phase conjugation. If you do phase conjugation or time reversal through a random medium where there is many scatterers, you can obtain very good focusing in space and in time. And now here, the thin focus point you have comes from the fact that it is no more the size of your antenna that give you the size of a focal spot, but it is the size of a random medium here through which wave propagates. And because this medium has a very large aperture, you focus very well, like if you have a lens whose size is the medium itself. This is a magic theorem that makes that you can focus very well through a random media, better than if you have nothing in the medium, just free space. Now we have used this to make a long time ago time reversal communication through a random medium, but it was done with ultrasound. We put 5 antennas very close one from the other, typically at 1 wavelength, which is quite close. And here we have a set of antennas, and we learn the response of each of these points from this set of antennas. And with time reversal, the response to focus not only on one antenna, but on the 5 antenna. And if you have possibility to focus on each antenna without secondary lobes on the other antenna, you can create orthogonal channel through the medium. And we can increase a lot telecommunication through this medium, but this works only if you use multiple antenna and broadband signal. And in this case, you can improve the number of data that you send to very close antenna. And this is time reversal communication. Today, this time reversal communication is not used like this, because today, when you work with Shannon capacity for MIMO, you know that you work with relatively limited bandwidth. And as you know, the Shannon capacity, the classical Shannon capacity, if you have one source and one receiver, depend on the power you receive on the receiver, and the signal to noise play a crucial role. And you know that now, if instead of having one source and one receiver in free space, you have a lot of antenna that emit and a lot that receive, you know that your Shannon capacity depends on something which is important, is this transmission matrix H, that related what you can send from each antenna here to each that receive. And you know that in the Shannon capacity, you see a matrix H DAG that appears. It is the product of the transmit matrix, but the phase conjugated matrix transposed. And you know that if you look what is the limit of Shannon capacity, it depends on the number of eigenvalue you have for matrix H DAG. And this number of eigenvalue you have for matrix H DAG is the same as the number of singular value that you have for matrix H. And in fact, the Shannon capacity depends on the distribution of your singular value that you have. Have you many singular value, and what are the weight, the value of this singular value? Is it the same weight or different weight? And for example, if you try to make communication with ultrasound in a medium where you have no obstacle, just free space, here, in our case, we have 6 singular value that tell you that you can have 6 independent channels when you try to focus from here to this to here. And you can have only 6 independent channels that receive 6 independent information. But when you put your random medium, what we found is that the number of singular value become much higher. And in presence of randomness, Shannon capacity increase because you have much more singular value. And even if you have 40 antenna by 40 antenna, here you have 34 singular value, which are strong. It means that you can have 34 independent channels. But all this channel has not the same weight here. And randomness is good to improve communication, but randomness is not optimal. And if you can change the randomness of a medium by putting somewhere an intelligent reconfigurable surface, you can increase this value of a singular value, and you can have a better Shannon capacity. And I will discuss this later. Now, all these ideas that we present, we first study them for ultrasound, and later we study them for electromagnetic waves in the gigahertz range, and we show that all this effect of focusing through random medium or through cavity were enhanced when we play time reversal. The main problem of 5G today, or massive MIMO, is that you can play with this with many antennas, but you need a lot of controller and a lot of antenna with a lot of electronic circuits. And this has a high consumption. It can help you to focus, and this is done in 5G. As you work with narrow bandwidth, you can say that you have only one spectral degree of freedom, and what you have to do is just to control the phase of your different signal to improve focusing. you can increase the focusing, but it is not a beautiful focusing because you are never in a city in a completely random medium where focusing is very good. And because your antenna are relatively far, the focusing is not so good. You improve energy efficiency by using 5G, some MIMO configuration, but you don't make a big jump. How to make a big jump? To make a big jump, you have to think of something else, which is passive control of wave by using tunable metasurface, and this is well matched for narrowband communication. This is the concept of reconfigurable intelligent surface that we begin to work in our lab 10 years ago by calling this smart mirror. Now people call this RIS or LIS, but in our lab 10 years ago, we pushed this technology. And the idea was the following. Imagine that you want to have a very good communication between two antennas, one at point A, one at point B. If the two antennas are very far one from the other, and if you are in open space, you receive on point B a very small signal coming from A because it decreases versus depth. Now imagine that you have a wall like a reflector, which is an ellipsoidal wall, where A and B are the two foci of this ellipsoidal wall. It's a magic wall. And imagine that point A sends a signal, a short signal or sinusoidal signal, and that you look what you receive at point B. Now, there is the direct path, which is not very strong if you are far, but all the energy you are sending in other direction is exactly put in phase by the ellipsoidal mirror at point B. And point B will receive all the energy that point A emits. There is no energy loss in this case. All the energy sent by point A focus on point B, and the level of signal is huge, and the signal to noise is very good. Now, in reality, when you are in a room with point A and point B, a room is not an ellipsoid. And if you work at one frequency, you know that you have some eigenmodes of a room. And if point A is at a node or an antinode of the mode, point A can try to emit and nothing will go if it is at an antinode. And if point B is at an antinode, there is no communication between the two. And you can have very bad configuration where A tries to emit and B tries to receive, and nothing happens because of the boundary which are not matched to B. Now, the idea we pushed 10 years ago was this idea. Can we put here a tunable boundary where the reflectivity of this boundary can be controlled electronically? And now, if instead of having a reflectivity, which, for example, 1 everywhere, same reflectivity, you have a reflectivity where you can control the amplitude of the reflection and the phase of the reflection. Can we build with a boundary where the pitch is lambda over 2, have a wavelength, typically it's 5 centimeters, every 5 centimeters if you work at 2.5 gigahertz, can you have a small reflector that you can control? And with this, can we control them to make that all the signal you send from point A, when it arrives at point B, is in phase? And the idea we have is the following. Imagine that when point A emits alone in a room where you have obstacle and boundary. If you are your intelligent surface, imagine that each point Ri of the surface, you can measure first the response between A and each Ri. This is one element of the transmission matrix, and you know all this response. It gives you all the phase and amplitude that you receive when A emits a signal here. Now imagine that B also can send a signal, and you measure the amplitude and phase coming from this spot. And you have in the memory all these elements which are complex numbers with amplitude and phase coming from A and from B. Now imagine that your reconfigurable mirror, you can electronically change the reflectivity to make that the reflectivity of this mirror is exactly the phase conjugation of the reflectivity of the signal coming from A. All the phase that you receive here coming from R on each point Ri, give you a phase term and an amplitude term. Now, if you create just H conjugated of this, you have created, which is called a phase conjugated mirror. All what you send from R, whatever is the complexity of the medium, refocus back on R. Okay, all the energy come back on R. Not very interesting for us. Now, if B emits, and now if the surface has a reflectivity, which is H star of Ri of B, all what you emit from B come back on B. Okay, it's this conjugated mirror, but it is not what we want. We want that all what we send from R come back only on B. And now, all the idea is that now if you create a mirror, which is the product of the two phase conjugated mirror, one associated to R and one associated to B, you have a magical mirror, because all the signal you will send, when they come on each point, they have some phase. Now, if you put H conjugated of this phase, and now if you put H conjugated of the other phase, if you look, all the elementary signal waves that come reflected and come back on B, now they are put all in phase when they arrive in B. Instead of being randomly distributed, where you have no signal, if this mirror is the product of two-phase conjugated mirror, all the signal you send that is intercepted by the mirror is put in phase on point B. And this can be huge if you have many elements here. But you have also communication, which is direct communication between R and B, going through obstacle. And this gives you also an amplitude and phase. And now, if you want that the two signals are aligned, you have just to shift this phase mirror by minus phi. And if you create a mirror whose reflectivity is this, it is a perfect mirror, will add its signal with the direct path to give you a huge signal on point B. And now you have created a kind of ellipsoidal room, even if there is a small amount of surface that do the business and that focus here. Now, this is nice, but can you control the reflectivity of your mirror in amplitude and phase? It is easier to make just a phase-only mirror where you just control the phase. You forget the amplitude. The amplitude plays a very small role in communication. It's better just to do phase conjugation. Now, this is a simplification. It is a mirror whose reflectivity is just a phase shift that you can control. Now, if you want to control a phase shift very precisely, it costs a lot to make a mirror that controls the phase. But the new idea we begin to work 10 years ago was to make a very simple mirror, which is only a binary phase mirror. It will, when a wave comes on it, locally the mirror will reflect the wave or without any phase mismatch, or just by putting a phase pi difference. It is like you reverse your signal or you don't reverse. It is a binary phase mirror, and you have the impression that it is a very crude approximation. But if your mirror has a size which is big enough with many pixels, if in your mirror you have a lot of Fresnel zone, and I will explain what it means. In fact, when you have just a binary phase mirror, this works nearly as well as if you have a mirror where you control perfectly the phase. And if you can do this, putting the best law here, all what you send is focus on B. Now, to understand this, why a two-phase mirror, which is a very simple mirror, works very well, you have to understand how a perfect mirror works. Imagine that you have a point that sends a wave here, and you have a mirror which is a phase conjugated mirror. That is to say, it's a mirror that refocuses back on this point. This mirror has a phase law that must be matched to the focal distance where you want to focus, and x being this position. And this mirror here, if it's refocused back on this point, it gives you a focal spot who has some size. The mirror has a size D, the aperture. You want to focus at depth F. And all the energy you send from here is concentrated in a focal spot. And because of this compression of energy, the amplitude of your signal increase like d square over lambda, the wavelength, the focal F. And you have what is called a compression factor due to focusing, which is d square over lambda F. And this compression factor that tell you how strong is the peak of signal compared to the signal you send here depend on d square over lambda F. And d square over lambda F, it is also the number of Fresnel zone. That is to say, if you compare the phase you have to come here with the phase to come here, there is a pi difference. And here, the number of Fresnel zone you have give you the efficiency of focusing. This is when you have a perfect mirror where the phase is perfectly controlled. But now, if instead of having a perfect mirror where you control the phase perfectly, you have only two phases, this reflection law can be approximated. You replace this by a two-state law. And just the mathematics show you that when you replace a perfect mirror by a two-state mirror, it is like you have the summation of a perfect mirror that focuses here, but you have 2 over pi, you lose amplitude, but you have now also, because of this rude sampling, also a kind of diverging mirror. Instead of making only a converging mirror, it is the sum of a converging mirror plus a diverging mirror. And when you replace this by this, what you receive at the focal point is less than here. You have 2 over pi because you lose something in the sampling, but you have a nice focal spot like the initial one. But now you have also energy in a diverging wave that give you side lobes. And the level of the side lobes is 2 over pi like this, but because all the energy spread in an homoetic beam with a ratio of 2, it is like you have 1 over 2. And when you compare the peak to the side lobes, the ratio of the 2 is 2 over d square over lambda f. And if you have an aperture which is big enough to have many Fresnel zones, you can have the ratio between the peak and the side lobes, which is 20. And 20 is a very good focusing. And when you have this works very well. And this shows you that if you have a metasurface or a mirror that contains enough Fresnel zone, you can control just by a two-phase system very well your beam, your focus beam. Now, I have no time, but this concept of what is the best mirror to make point A and point B well connected, this mirror has a pattern which is related to an holographic principle. If you have a point A that emits a signal and point B that emit together a signal, two sinusoidal signals, they make interference on this surface. But this interference is a set of hyperboloid. And this is what is called an hologram between point A and point B. It is the interference pattern that you receive here. This is just the intensity that has this shape. Now, what we want is not this. We want to have an ellipsoidal pattern instead of an hyperbolic pattern. And if we just measure the intensity coming from two antennas here, we have an hologram, but the hologram is not exactly what we want. We have to transform an hyperboloidal hologram in an ellipsoidal hologram. And there is a mathematical transformation. And if you do this, now suddenly the surface will learn how to connect A and B perfectly. This is something on which we are working. But today, we don't use this concept to work with our reconfigurable intelligent surface. We use something simpler. First, we have to bring this binary phase intelligent surface. To build them, what we do is we put on a surface a small electromagnetic resonator, which are very flat. And you know that if you have a resonator that resonates at one frequency, the one you use, for example, for Wi-Fi or for 5G, you know that when you send a wave on this resonator, just at the frequency of the wave, you will have a shift of pi/2 because of the resonator working at the frequency. And now your signal is shift of pi/2. And now if you have a ground plate, there is also a shift of pi, and there is a reflected signal, and there is a second shift of pi/2. When you put your element exactly at the resonant frequency of your microwave, this is a state 0. The signal is reflected without any shift of phase, 2 pi. But now, if you just change a little bit the frequency of your resonator by coupling this resonator with a parasitic resonator through a diode, now you shift the frequency of your circuit. And now the same signal will be shifted pi, and this is just a two-stage binary surface. It's very easy to do this. And when we have built this, we improve the technology to find a good way to create this small resonator. And now we put many of them in a room. And the first experiment we have done, it was a long time ago, was to put a source in a room, and in another room you have an antenna, and you have your intelligent surface. Now, instead of learning the response between the source at each point and the antenna at each point, which was too long to do, we just used an iterative algorithm to try to change the configuration of your state to learn how to focus here. And we just, because it's a binary system, we just begin with one reconfigurable intelligent surface in one state. We look what we receive on your receptor, and we change 1 pixel, and we iterate this. And we learn quickly how to focus on the surface. We can do it if there is not too much element. And you can see this here. Fabrice Lemoult here has an antenna. There is another antenna in another room. And here you have your configurable surface. And here you see the pattern of plus and minus that make that if you move your antenna in a bad place, the system learns how to focus on it. And it takes some time here because it was with a very old electronics, but very quickly you obtain a maximum gain. And the system has to, in real time, learn always how to better focusing on your antenna. We have begun by this. And when we begin by this, after people tell us this is nice because it is between two antennas. And after they tell us what happened with MIMO. If you have many antennas that transmit, many that receive, is it useful to have also a reconfigurable intelligent surface? And we show this. It was in my office. In my office, we put this kind of intelligent surface. We put a series of antennas here and a series here, for example, 5 antennas. And we decide to look what is the Shannon capacity that we can reach in this room. And as I remember you, the Shannon capacity depends on the determinant of H tag. We depend on what is the number of singular value that you have for this matrix H. And it depends on the configuration of the sigma value, the singular value. And when you have a room which is relatively random, you know that there is one singular value which is stronger than the other singular value, but the other decrease. It is not too bad because you have 5 singular value when you have 5 antennas, but it is not very efficient. The best will be to maximize Shannon capacity to have equal singular value. And what we make, that we try to maximize in a MIMO configuration, the set of pixel we have here to maximize what we call the entropy of a singular value. We try to find a way to put all the singular value at the same value. this maximizes the Shannon capacity. And when we were able to do this in the room, relative after 40 iterations, we show that we can send much more information in a MIMO technology. This is MIMO, but we can use also this for MIMO mu. We don't want to send this to collaborative antenna, but to different antenna. And we can try to improve the room. When we have done this work, it was in 92 that we put first patent on this, in 94. Nobody in the telecommunication people have seen this paper. And it was only when we begin to work on MIMO with reconfigurable intelligent surface, and when this paper with Marco Di Renzo appears that begin to speak of this, that people begin to be interested by the field 2 years ago. And we were very happy when 7 years after we show our first experiment, MIT make a big publicity to say smart surface for smart device. And in fact, they present exactly what we have done, but some years ago, before, to show that they can improve from a lot what you can make. Now, what I want to tell you is that we have developed this. Now, many people are interested by this. This RIS surface has to work together with base station and with the receiver, and to optimize all this is complicated. The holographic principle will help to optimize this because it can make that reconfigurable intelligent surface may become in the future autonomous. They don't need to interact too much with base station and the receiver, but this is a step for the future. When we have done this, we decide also to create a startup that we call Greener Wave. And in fact, Geoffroy Le Roset, which is a fantastic researcher that worked with me on this idea, he moved to the startup and began to develop different kind of reconfigurable intelligent surface in different frequency range, and till very high frequency. And there are, in fact, many applications, not only telecommunication and radar. And recently, they built at 28 gigahertz a very nice reconfigurable intelligent surface that contain 1,600 pixels, and they can allow you at 28 gigahertz to improve communication in rooms. You have a transmitter, you have a very bad communication, and you begin to play with intelligent surface, and you can increase the amount of information that you can send in complex configuration of room with this. Well, my conclusion is here. We think that reconfigurable intelligent surface is a big step because the size can be relatively large and the angle on which your receiver sees the reconfigurable surface become huge. And because of this, the compression factor you have, it's much more bigger than what you have in 5G today. In 5G, we say we have a better energy efficiency. But if you look at the number, they are poor, between 2 and 10. When you will use the reconfigurable intelligent surface, if they cost not too much, you will have an energy efficiency that is of another order of magnitude. And this is the future for reconfigurable intelligent surface. Thank you.